Developing using some random.
Yeah, it was.
Xcode.
It wasn't
It
Apple
wasn't
verified
really
Xcode. So like
Xamarin or something like that.
No, it was Xcode, but it was redesigned. So like with people running like Hackintosh, it was built into the Xcode.
Oh, okay.
So people thought they were developing with regular Xcode.
I get it.
And then they
But it
were
was
submitting
tainted.
their apps,
Yeah.
and they were getting approved, but Apple just found out.
And
I see.
they had to take down 5 apps already, and that was before.
And
they
what
realized
does
what
the
it is.
worm do?
They don't know yet.
They just took it down because there's a worm.
Yeah, there's.
It's like burning down your house because you find a caterpillar in the driveway.
Well, it was something about stealing user data.
Okay, so it does something bad.
Yeah, something bad. They just wouldn't say what, and that just makes me think it's bad.
Okay, so it's actually funny. So they take down my video for copyright stuff. I think wouldn't this be like the dinosaurs and stuff? And look, it even says.
Well, you're citing it though.
Yeah.
The other thing said Travel Channel on it.
Well, YouTube does it based on like sound and that's how they're
I got you. So if they knew about this, they would pull it down too.
They don't go like on picture based copyright.
Yeah, it's fine.
Sound based.
It's understandable. It's understandable. All right. So what is the difference between multitasking and multi-programming?
Multitasking is the human perception. Multi-programming is what's actually going on.
Yep. So, or you could say it's for the most efficient way to do it from, or an efficient way of doing it from the computer's perspective would be multi-programming. Multitasking is keeping the human being happy. So it depends on perspective, right? Or you can, a couple other ways you can maybe say this. You could say multi-programming is the act of having more than one program running on a computer at the same time. Whether it's physically running at the same time if you have multiple core CPUs, or seeming as if it's getting CPU time at the same time. Multitasking would be the act of a human being expecting multiple programs to be available to them quickly while they're using their computer. Has very little to do with what we care about, what's happening under the hood. It's really about flipping between applications and feeling like they're up to date and that kind of stuff. So like if you bring your email to the forefront, for example, let's say your email's open on your computer and you bring it to the forefront and it only checks for new email when you bring it to the forefront. That probably wouldn't make us happy. Typically, if we're flipping over to our email, it's because we want to just check to see if we got any new messages in our inbox in the last 10 minutes or something like that. So we would expect at a glance to be able to see that, right? So that would be kind of the multitasking side of things. Let's see. Skip that. Well, user mode versus kernel mode. This is just more of a security protection in operating systems. When your operating system is working in kernel mode, it can do extra special, horrifically damaging type stuff. When it's in user mode, it pretty much stays within that user's little ecosystem. So a user could delete their entire directory or something like that, but really can't damage the rest of the operating system. Once you're in kernel mode, you kind of have to pass some checks and balances because kernel mode lets you pull off some other stuff. So they're kind of showing, this example here where if there is a system call that exists in kernel mode where you need to have admin privileges, let's say, to do something. So we see this on Windows when sometimes asks, this requires administrator privileges. Do you want to put in your password? You're kind of giving it permission that what I'm about to do is something that I've approved, because it's about to use your operating system in kernel mode to do something that potentially could be harmful. All right. Process management. So again, this is getting us kind of a high level of these different widgets that are in our operating system. So when we think about a process, when we think about so let's say a process is the data structure for holding a computer program that's running on your computer. That's what a process is. So when we double click on Microsoft Word, a process is born. And inside of this process, actually potentially several processes, but let's just say one process is born. In this process data structure, in this object, we're going to be loading the low-level code that is the Microsoft Word program. That's one thing that's going to be in there. So we're going to have a collection of magic tricks that need to be executed in a certain order. We're also going to have something called the program counter. That is, which magic trick happens next. All right, because we want to think about our CPUs as kind of like Pac-Man. It just sits there and eats. Right? So, it does it based on sound. So I can make Abba. Abba, 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 Abba. Is that Pac-Man? Yeah. So we'll see if that gets flagged. So in any case, we want to think of our CPU kind of like Pac-Man, where it's just sitting there eating magic trick after magic trick after magic trick, and the program counter is that integer that tells us what is the next magic trick to feed to the CPU by our CPU scheduler.
What if it hits a ghost?
That makes sense? What if you hit a ghost? That's called an interrupt. Okay. All right, so now we'll talk a little bit more about low-level languages later when we actually get into the process management here. But understand that a program counter doesn't necessarily just go linearly through a program. It's not always line 0, line 1, line 2, line 3. You might get to an if statement here, conditional, a branch in a low-level language. And if it's one thing, maybe you go to line 4. But if it's another thing, maybe you go to line 17. So the program counter could jump around in the program. So it's always pointing to or keeping the index of the next magic trick that the CPU should eat. Make sense? So that's what a process is. We just want to think about it from a programming perspective. It's just a data structure that holds the pieces of information surrounding a program that the CPU is going to need and the CPU manager is going to need in order to effectively process that program.
Have you been hungry lately when you come to this class?
I've been hungry?
Yeah. Well, last one you talked about, you showed the video of you eating.
No, I eat breakfast here at 7:30. We're good.
Now you're talking about eating Pac-Man?
No, Pac-Man eating.
Pac-Man eating?
Eating Pac-Man is just sick.
Tuesday.
All right, so things that the process manager is responsible for: creating and deleting user and system processes. So when you double-click a Microsoft Word, new processes are created. When you close Microsoft Word, processes are killed. It's got to do that kind of crap. Suspending and resuming processes. So when something, this can happen in a couple different situations. It can happen when we interrupt a process to go get I/O, something like that. It can happen when we minimize an application. So minimizing an application, maybe certain aspects of the application are considered to be turned off. Other aspects of the application still need to stay active, that kind of stuff. Providing mechanisms for process synchronization, process communication. So these two things, these deal with having multiple programs on our computer that need to somehow stay in sync with each other. Maybe it's a chicken or the egg problem. We have two programs and this one can't do its job until this one's finished doing its job. So that's another thing the process manager has to do, is make sure as it's scheduling when these guys get CPU time, when we're going to feed stuff to Pac-Man, that we don't feed Pac-Man out of order, right? Take these pills with food, so you got to give them the food first, then you take the pills, right? Or I guess you take them at the same time. Probably not horribly dangerous to take the pills first, then eat some food, as long as it's soon.
I do it all the time.
Check with your doctor. Put the disclaimer in. Process communication is probably the bigger idea where we have something called IPC. You maybe have seen this. You probably saw it when you read chapter 1. Big I, big P, big C. That's inter-process communication. So we have mechanisms in our operating systems that provide various ways for one process, one program to talk to another process. All right, whether it's sharing some piece of information among multiple processes, whether it's letting this guy know that a certain event has occurred, all sorts of stuff like that. So we have ways of making other processes aware of information, either directly sending them things, or maybe it's almost just like, hey, I'm done. So we have things like signals. We have something called semaphores. Those are good ones. Shared memory, things like this that we'll talk about when we get to our section on inter-process communication. And then lastly, a mechanism for deadlock handling. In reading chapter 1, anybody remember what deadlock was?
acting in the or Marvel's Agents of S.H.I.E.L.D.
I think it was in
That's
chapter
fine.
1, wasn't it? Doesn't sound familiar? All right. Well, okay. So in any case, deadlock deals with. Okay, so we talked last time, I think last time about with memory management. So all these different resources in our computer are all sharing this one monster, memory, right? Memory is incredibly important in our computers. Lots of stuff are important, but memory is really shared by so many resources. So we can imagine that the dude who's in charge of managing memory has a pretty important job in our operating systems, right? So the idea of deadlock is when we have a whole bunch of programs running our computer at once, that memory manager has to get as many of them shoved into memory as possible. And most of the time, we're not going to shove the entire program into memory. Just kind of the next 40 instructions. Let's just say that as an example. Okay? So when you need instruction 41, that means that something needs to be swapped into memory from virtual memory. We'll talk about the details of that later. But the idea of deadlock is when you have two programs running on the system at once, and you have, let's say your memory is full, just as a simplified example. And this program needs this guy, so it's swapped in. This program needs the guy you just swapped out, so he's swapped in. This guy needs the program, the instruction you just swapped out, so he's swapped in. That's deadlock, where you just keep swapping things in and out of memory, and they're things that these two guys both need. Okay, and that has to do with the generic, almost threshold algorithms that have to exist for the memory manager to decide, okay, well, this guy needs something that's in this virtual memory. What do I get rid of in real memory to make room for this guy? So he's having to make a best guess at what is safe to remove from real memory. And if he makes a bad guess, deadlock can occur. Make sense? The hope is that deadlock only occurs once and the very next swap fixes it. But in a situation where you don't have enough system memory, where you have very small portions, let's say you have not very much memory in your computer and a whole lot of applications open at once, you can create a scenario where deadlock is basically unavoidable. And that's where you sit there and your computer doesn't seem like it's doing anything. You just hear clicking and stuff. You just hear it working, and the gears are turning, but it's not doing anything. You can't function. That's what's really happening under the hood. Something has occurred like that, where some process can't finish. Make sense? So that's the concept of deadlock, and we'll talk about deadlock handling and deadlock avoidance and that kind of stuff.
And that pretty much only happens when you have memory issues? Or could it
It's also resource sharing. Yeah, so a lot of times when you really hear a lot of sounds coming from your computer, it deals with a hard drive, where you have two things that are. Good example of this would be if you've ever downloaded two large files at the same time on your computer, but in separate, not in one batch. If it was going to take 20 minutes for file 1 to download, and it would have taken 20 minutes for file 2 to download, time for both of them to download is like 60 minutes. You know what I'm talking about?
Yeah.
Okay. The reason is because it's trying to manage both of these guys wanting access to the hard drive. So it's letting this guy write a couple of bits, and this guy write a couple of bits, and this guy write a couple of bits, and it's spending a lot of time switching control back and forth between two different processes. That kind of stuff. So the concept of deadlock would apply to things like that. Okay, so resource sharing, but it's probably mostly applicable to memory because that's where we see it the most. Yep.
Now, as we move as we move into faster solid state drives, would there be less mechanisms for deadlock handling because loading things from virtual memory then would be faster?
Just because it's faster doesn't mean you don't still have to have the mechanisms. That the performance would improve, but I think I don't think the mechanisms have anything to do with the performance of the underlying thing unless it's a drastic difference.
Okay.
I mean, solid state are faster than mechanical drives, but not drastically. We're not talking 300 times faster.
Because I noticed with the new Samsung solid states that are coming out with the new new like stacking technology they did, they're almost as fast as like regular RAM.
Mm-hmm. Well, and we're going to move towards that. I mean, there isn't a great reason why we can't have. I mean, they have something called RAM disks that have actually been around for a long time. There isn't a great reason why you can't use part of your system memory as a hard drive. So when your machine's first booting up, it takes a little bit longer because it's basically copying a hard drive into RAM. But that part of the hard drive is really, really quick. Something like that. So what's really, why aren't our hard drives made of system RAM? Cost, right? It's expensive. Even though system RAM is cheap, you try to get 2 terabytes of system RAM, not so cheap anymore, right? At least not comparatively. So it's that type of thing. Let's see. So then memory manager, we've already talked a bunch about this. So here we've been talking about process management, the idea of managing our programs while they're running on the computer. Memory management, this is the idea of controlling that resource that is our memory. So all data in memory before and after processing. So when you've gone through a program, variables get set in memory and stuff like that. Before a program has been run, parts of that program are loaded into memory, that kind of stuff. All instructions in memory in order to execute them. So our system memory is like kind of a staging area for our programs who are getting ready to get onto the CPU. All right, so we keep their instructions, the instructions the CPU is going to eat, in fast memory. That's our system memory, before we move it to faster memory in preparation for the CPU consuming it. Okay, because we don't have tons and tons of faster memory. So we can't put all the current programs that are on the computer into faster memory. We can't put it into the L3, L2, L1 cache or the registers. It doesn't work that way. We don't have enough room. So we have to house them in a pretty fast place where we do have room. And we we mentioned virtual memory here a few minutes ago. We don't even house all of it there. So we keep a majority of our programs in virtual memory, which is essentially the hard drive, just waiting to be swapped into real memory. We hold in real memory what we hope is the stuff that's going to be imminently needed by the CPU, the process scheduler. And then we transition those things into our cache memory and our faster memory as the line starts, as that process gets closer and closer to the front of the line. Because the CPU actually eats off of the CPU registers. The faster the memory, that's where the CPU is actually doing its consumption. Let's see. Memory management determines what is in memory when optimizing CPU utilization. We already said that. Okay, so beyond that, bookkeeping. So the memory manager has to keep track of who is in memory and where. So if you went to the memory manager and so when the CPU has an interrupt and says, okay, I need, they're called pages when we get into talk about memory manager specifically, but I need the page with instruction 32 on it for this program I'm about to run. It goes to the memory manager. The memory manager checks his books and says, he's not in memory. Okay, so I need to go swap him in. Or he says, oh yeah, you can find him over at address such and such. Okay, so this guy he's booking a hotel. And he has to keep track of all of the room bookings, who's in them, and that kind of stuff. Let's see, deciding which processes of data to move into and out of memory. That's the whole swapping thing. Okay, and just go down the path a little bit from a computer science perspective. One of the things we're going to talk about there is various algorithms for making that decision. Does that make sense? And some of them are guesses. So one thing that we're going to end up talking about in here that hopefully will end up will be interesting to you is some of the decisions we make in operating systems are far less scientific than you might expect them to be. Sometimes it's just like best guess. In fact, a reasonable approach for swapping is just random. It's like, okay, I need to bring something into real memory. I need to get something out of, I need to bring something from virtual memory into real memory. So that means I need to get something out of real memory and put it back into virtual memory. Which thing do I do? Well, let's just roll the dice and hope for the best. And that's actually a valid approach. Okay, if you don't have any other given information. Otherwise, some other approaches are like, we have something called the dirty bit. You'll probably love that, Doc. Yari likes it. So we have something called the dirty bit, and so that when a page was recently accessed, it sets a bit saying that this guy's the dirty bit says I was recently accessed. Okay. Well, we can look at that two different ways. We can say since he was recently accessed, he's likely to be accessed again soon, or we could say since it was recently accessed, he's probably not going to be needed soon. We can go either direction, right? So again, you're making algorithm decisions based on a best guess. All right, and then beyond that, you also have to think about the nature of the operating system, or the nature of the use of the operating system you're writing this memory manager for. If it's a server-based operating system, you're going to make decisions that maybe give you better total throughput for multiple users using the system at the same time. Where if it's a single user operating system like Windows or the Mac OS, we're going to be making decisions based on what's going to make our single user happier, right? See, a lot of us have, how many of you have ever, downloaded the server version of Windows or the Mac OS, probably more common on the Windows side, but they're the Mac OS server and use that as your main operating system. None of you have ever thought that would be cool? Because what ends up happening sometimes is you have as an example, Windows 7 came out, and then Windows Server 2012 came out after 7, right? So one might say, oh, well, I'm going to grab that because even though it's the server operating system, it's actually a newer operating system. So you can kind of see that logic maybe, but the reality is that operating system has less focus on making an individual user happy and more focus on making many concurrent users happy. Now, you might not be able to tell the difference, so it might not necessarily be a horrible thing, but understand that different decisions may have been made under the hood because it's a server operating system as opposed to a single user operating system. So these are all things that go into this moving target, and a lot of times we're just doing best guess. So a random just eeny, meeny, miny, mo type thing might be literally an acceptable approach and in some circumstances give you superior performance. It's the matter of the luck of the draw. Okay, did we roll the dice well today or not? Let's see. Okay, this is all stuff we've said. So punchline, well, obviously, we've said many times, memory management's very important. Memory is very important. And why is it very important? Because everything on our computer uses it. Everything. The programs, the other resources, they all use memory. So it's an important dude. Not everybody uses your scanner. Okay, so the driver for managing your scanner is lower on the totem pole. It's kind of like I don't know, like the mayor of a town in Podunk, Texas, something like that. As opposed to the person who runs the most popular bar in Podunk, Texas. He would be much higher up on the totem pole. Let's see. Storage management. Okay, so memory management deals with managing the fast storage areas. Storage management is going to deal with our longer term type stuff. So one of the things, this has to do with our driver system. We abstract the physical properties of local storage. So whenever we're storing stuff on a hard drive or a USB stick or burning something to a DVD, no matter what the final media is, we still think about these things in terms of the data structure that is the file, right? We say we have two animals, right? Files and directories. So all of our stuff is organized in files and directories. Those are two, from a programmer's perspective, two data structures. What does a file hold on to? Well, it's probably going to hold on to the crap in the file, right? It probably also is going to have a format associated with it. What's the structure of this file? Is it for, is it FAT32 format, file allocation table 32? Is it FAT16? Is it NTFS? Is that UFS? What is the file system that this particular media is using, and how is this file compatible with that? Now, whenever you are working with a file, do you have to worry whether this file will be compatible with the file system you're putting it onto?
You have to be worried that you don't have to be worried about putting it on there. It's actually using the file. You may not be using the correct operating system.
That's it. So the file systems themselves drop down to the common denominator that is the file, right? There's very low risk that we're going to have a new file system that comes out that says we no longer deal with the old school file. Okay, we now know how to store a new kind of data structure, something like that. I don't know if that'll always be the case, but at this point, we don't necessarily see weaknesses in files. But the reality is, files have been around for a long time, haven't they? Wouldn't it be neat if because for instance, some of our modern file systems that we'll talk about are like these things called journaling file systems. How many of you have ever heard of a journaling file system before? Okay, do you know what it means to be a journaling file system? Or what's the perk of journaling file systems? You can roll back. Something bad happens, a journal entry is made every single time something happens, every single time an event occurs on the hard drive. So if something bad happens here, we can roll back to an earlier journal point and rebuild our data from there and get back to when things were still okay. All right, well, go ahead.
Is that similar to, or the cause of, like, Microsoft Office being able to recover documents from previous days?
No, I mean, it's similar goal in mind, but different approach. Because, I mean, but along those lines, we would agree that we have all sorts of approaches at not losing our data, right? So, modern things today, we have the cloud computing stuff like Dropbox or Box. I think you use the Microsoft. Yep. So, Google Drive, things like this. So these are all tools that are meant to, anything you put in a certain folder gets duplicated in the cloud without you having to worry about it. Last time, I think I mentioned something about RAIDs, right? Hard drives kind of set up so we have physical hard drives, interestingly connected to each other in a special way, whether it's through hardware or software, but in such a way that if I write to this hard drive, that same information automatically gets written to this one without me having to think about it. Okay, so these are automated type things, all with the goal of being able to recover data. Okay, well, if we think about the concept of a journaling file system just at the high level, they had to design the file system so that it had this additional overhead of keeping track of everything that's ever happened on this file system so you can roll back. Why didn't they change the definition of a file? Why shouldn't a file keep track of previous versions of itself? Short answer is maybe it should, right? But if you are generating a file system and you'd like that file system to have the feature of being able to recover, you have two options. You can build that into the file system itself, or you can change the standard of the animals you're storing. Well, I can conform, or I can try to reinvent the wheel. Maybe reinventing the wheel would have been a better idea. Maybe it'll still happen. Okay, but in today's world, we don't really see a major weakness with files, so what we're going to do is we're going to add that overhead into the file system itself rather than change our shared widget that goes across all file systems. Kind of make sense? All right, so again, the pattern I want us to see here with all these discussions is it's the exact same thing we do with real life problem solving. Operating systems, computer programming languages, it doesn't matter what we're building. We're applying the same kind of problem solving we do in real life. Sometimes our decisions are made out of convenience rather than out of optimization. Right? It's like, well, I want to put an in-ground pool in my yard, but I can either move and get a bigger yard, or I can get an above-ground pool that will fit. Make the decision. Maybe the above-ground pool is lower quality, it doesn't have as many perks, but you don't have to move. So we make decisions like that all the time, and the same thing happens really very often in operating systems. We're rolling the dice a whole lot in operating systems. Let's see. So the file abstract type, if you will, and then we have to have some mechanism for talking to the various mediums, where there's disk drive, tape drive, things like that. Modern operating systems use a system of drivers, right? Historically, that didn't exist. Historically, the operating system itself had to be taught how to talk to each device, so it had to be written into the operating system. Now we see it less today. I mean, we don't see new storage technologies come out that often today, right? But not that long ago, in like the early 2000s, late 1990s, you had floppy disks, then you had things called super drives, and you had zip disks. And Iomega made the 100 megabyte zip disk and the 250 zip disk. Then they had the Jazz drive, which was a 1 gigabyte and a 2 gigabyte cartridge. So you had all these different companies competing.
Things were getting out of hand.
So if you just bought Iomega's brand new zip drive here, but you had an operating system that was made 2 years ago, it's not going to work because it didn't know about the zip drive, right? Well, so that's why we started having things called drivers, which are just pieces of software that sit between the operating system and the hardware itself, that implement the various features of a piece of hardware in terms of the generic capabilities of the operating system. So an operating system, just generically saying, maybe knows how to read and write from a disk, okay, from an external storage thing. So if we're going to write a software driver for specialty storage device that we just invented, if we're going to write that software driver, we have to do all sorts of all the magic tricks this guy knows how to do. We have to implement them in terms of the 2 or 3 magic tricks that are implemented at the operating system. That make sense? That's the job of the driver. So kind of a fancy name for, I'm a little piece of software that just converts between this dude's language and this dude. All right? So when you go in, I think we mentioned last time, like the NVIDIA or ATI graphics cards, you first pop it in, screen looks like crap, right? Because it's using the default lowest common denominator VGA driver that says, hey, I know how to light pixels. All right? Then you install the NVIDIA or the ATI, super driver that does 4 zillion things in terms of the capabilities of that VGA driver, most of which are leveraging hardware on that graphics card. It's telling the hardware in that graphics card to reformat a whole bunch of stuff in such a way that it could feed it to that VGA controller in a way that it understands. So it's all a conversion process. So conversion that happens at the software level is often slower than conversion that happens at the hardware level. Make sense? And this idea of conversion we see all the time. How many of you have a TV at home, either cable TV or UVerse or DirecTV or something like that, right? We all have a set-top box, right? The set-top box isn't just there to look fancy, right? What's the set-top box for? Well, it decodes the signals that come in. As we get more and more channels, last year we had 100 channels, now we have 200 channels, but you know what? They never changed my satellite dish. So it's the exact same communication portal. They're just shoving twice as much crap through it. Okay. Well, how do you shove twice as much crap through the same communication channel? Well, you have to compress it. Okay. Well, that means if it's compressed, I have to decompress it before I can see it. Well, decompression at the software level, they would be slow. Decompression at the hardware level is very fast. All right. Kind of makes sense. So that same little magic trick, converting things from one format into another, is stuff that we do all the time in our problem solving. Make sense? So I'm just going to keep drilling that point home in every class that you have with me. 100% of my classes, I talk about how human problem solving plays into all this stuff. Dr. Locklear talks about the grand ideas of computer science, how all of these different courses all have to do with the exact same stuff. All right? So our entire field, computer science, is all about us convincing ourselves that we can talk to this stupid alien that's a computer. Right? They have very limited capabilities. Yet we tend to think of them as being up here and difficult for us to communicate with, when really we're too smart for our own good. We have to dumb it down for these guys. Let's see. So access control, this all deals with the resource management stuff. You know, we can't, if we have two guys trying to access the hard drive at the same time, we allow it, but, you know, from a convenience perspective, but it certainly hurts performance. It's probably our easiest way as users to see performance slow down on our computer by trying to save two large files to our hard drive at the same time. Let's see. That's not a big deal. Same thing. All right, so this is just a rehash of something we've seen before. So registers, in terms of size, less than a kilobyte. Cache, greater than 16 megabytes. Main memory, I don't know if I'd say greater than 16 gigabytes, but whatever. Disk storage greater than 100 gigabytes, but you know. But then we look at access time. This is the more important thing for us. So registers have really low latency, so the amount of time it takes to access those things, it's very, very, very fast. This is in nanoseconds. So a quarter of a nanosecond to access a register. A half a nanosecond to access our cache. 80, so it's 160 times slower to access what we call fast memory than it is for our cache. And 320 times slower than our registers. Disk storage, a little bit slower.
No, not at all.
So important thing from this slide is to understand that step up. And they probably could put dollars somewhere in here too. They didn't, but you know, you get the point. Go ahead.
So with the access time nanoseconds there for a magnetic disk, is it similar for a solid?
The solid would probably be faster, but it would still be a number much closer to this than to this. Okay, okay. Many zeros. Okay, not 1 0. Then we also see bandwidth. So this is the amount of megabytes per second. So which is actually interesting because these guys have really low latency if we want to think about this in terms of like our internet connections. How fast can we communicate with the resource? How fast can we grab stuff from that resource once we've started communication? All right, so we can access really quick. This is like our ping rate, if you will. When we're grabbing stuff from our registers, we pull it in at 20,000 to 100,000 megabytes per second. Really fast. But we don't have that many megabytes. Okay, so we're actually pulling in 32 bits at a time, let's say, at 20,000 megabytes per second. Make sense? That's the speed limit. And then it goes down from there. So we see disk storage, we can get up to 150 megabytes per second. Not to be confused when we see like serial ATA speeds of 6 gigabits. Little b, not big B. Go ahead.
What happens when your download speeds exceed the speed of how fast you can write your hard drive?
You tell me. What based on what we've learned in here so far, what will have to happen? We've talked about this technology already. So his question is, when our hard drive can write at speed X and our download speed on the internet exceeds speed X to the point where the hard drive can't keep up, what do we need? Need what? Better hard drive. Okay, well let's say we don't have that better hard drive yet.
A credit card to get a better hard drive.
They don't make it yet. Doc has the best hard drive out there and the fastest internet. So, but the problem is that your internet has now exceeded your hard drive write speed. We're not there yet, but he's provoking a question, what if we were? What would the solution be? Okay, one solution might be to throttle our internet connection, right? Let's just dumb it down for the hard drive. From a human perspective, that doesn't. Whenever we associate the word throttle with internet speed, we get a bad taste in our mouth. Okay, we don't like that. What's another option based on what we've talked about in here? Buffers. Yeah, we've talked about buffers in here, which is a generic phrase for put it in memory so that we can read from it at our own pace. So you just need a big enough swimming pool here of some kind of memory, something that's fast enough to receive the speed that's coming in, right? Okay. The more impossible question to answer is, what if it exceeds the speed of our registers? This guy. What if it exceeds that?
Then you're really
Okay. Well, if it exceeds that and our registers are still 32 bits, computing no longer happens. Okay, we're in a whole different ballgame. Okay, so we'll stop there. I will not give you assignments today, but you will have one Wednesday. Sound good? Because we're out at 55, right?
Yeah.
Okay.
So I just realized on my phone.
Hold on, so let me stop this and let me